Assalamu alaikum wa rahmatullahi wa barakatuh. I am Dalia Musa. I work as a lecturer at Al Farat Al Wasat Technical University. My research work is enhancing the control strategy of fault write-through capability for a grid-connected wind farm using voltage source converter high voltage DC. This research contains many items as shown on this slide. The first item is the introduction. Global warming is caused by the burning of fossil fuels and the release of greenhouse gases. As a result, governments are looking into using green energy instead of fossil fuels. Wind technology has become a viable alternative for generating electricity due to its availability. However, as the number of wind farms connected to the grid grows, the grid power's quality and voltage stability become a worry. High voltage DC is the preferred choice compared to high voltage AC to transmit bulk power over long distance. Due to use of two conductors instead of three, are there more losses in high voltage AC system. Due to AC lines' reactive characteristics, there is no such loss in DC cables because of zero frequency in DC links. In this paper, a control strategy for 40 megawatt offshore wind turbine connected to the grid via high voltage DC link is presented. The problem statement of this research is reduce the power losses in high voltage transmission line due to AC lines' reactive characteristics and the cost of the conductors. The fault ride-through capability of the wind farm and increase the reliability of the system. The objectives: design a simulation model for a 40 megawatt wind farm connected to the electrical grid high voltage DC by using BSCAD EMTDC software. Reduce the losses power by using voltage source converter high voltage DC for wind farm instead of high voltage AC system to transmit bulk power over long distances. Propose control strategy which enables the wind farm to ride through fault, thus increasing the reliability of the system based on Germany's standard EON grid code. The methodology of this research is the power system presented in this paper using wind farm modeling 40 megawatt wind farms using 20 sets of 2 megawatt wind turbine, and the fault ride-through for the wind farm is done via voltage source converter high voltage DC system. By investigation to stage 6 pulses in states insulated gate bipolar thyristor IGBT at the generator and the grid side of the power system. Two voltage source converter stations are simulated in BSCAD software as shown in this figure. A control strategy is proposed to improve the fault ride-through capability of the wind farm, thus increases the reliability of the system based on German standard EON grid code requirements. This control system can be used for offshore wind farms connected to the grid where the wind farm is able to continue its operation without disconnection during the fault times. This ability makes the wind farm more reliable, especially when wind farm become the main source of power in the network. The changes in the voltage is needed to be in acceptable area. The EON grid code requirement for duration of voltage sag is presented in figure 2. The aim of this paper is to control the voltage to stay in area 1 as shown in this figure. The output power of the turbine can be calculated via this equation as shown in this figure, in this slide. The AC three-phase voltage in generator side are converted to DC voltage in DC voltage in DC side can be calculated as following, as shown in this equation. It is shown that when alpha is equal to 90 degree, the DC voltage is equal to 0, and when alpha is equal to 0, the voltage in DC side is maximum. The firing angle in converter is determined by the changing the firing time of the IGBT in generator side. The firing time for IGBT valves and fixed permitted to transmit the external power. The active and reactive power in DC side can be intended by using the following equation. The voltage control strategy for this research is: control strategy is shared between stations in order to improve the fault right-through and voltage regulation for the wind farm. Active and reactive power generation by wind farm is needed to be controlled during the fault times. In the reactive side, the power is controlled and wind farm inject reactive power to the connection point to increase the voltage and reduce the voltage side sag in the wind farm side. Active power is controlled by controlling IRQ, and reactive power can be controlled by controlling IRT. Figure 3 and Figure 4 show the control strategy of reactive side. Simple PI controller is used due to its simplicity in design. The reference current generated by PI controller then RP to DQ to ABC converter components to generate the three-phase reference current. Moreover, using a pulse width modulation, the firing pulses for IGBT will be generated. However, grid side voltage is needed to be controlled to reduce the voltage sag in DC link. Figure 5 shows the control strategy used in the grid side of the transmission system. In Figure 5, VRMS is compared with the reference VRMS and VDC is compared with VDC reference. Using simple PI controller reference voltage for pulse width modulation is generated. Three-phase reference voltage is then generated using DQ to ABC converter. Rotating angle for QD to ABC converter is generated through PLL component. The simulation results: the wind turbine controls the inject angle using the power output, and the generator speed of the generator. Figure 6 show the generator speed and pitch angle during changing in wind velocity. When the wind changes to 10 second inject angle then will increase to reduce the rotor speed and maintain the rotation of the shaft in the acceptable speed area. As shown in this figure, figure 6, during the time that wind speed is changing, the inject angle will change respectively in order to reduce the change in the generator rotor speed by decreasing the change in the rotor speed. Wind turbine is able to generate more constant power with less effect on the power transmission. The voltage side, ingress side, and wind farm side for fault are shown in figures 7 to 10. Conclusion: the fault ride through capability of 40 megawatt offshore wind farm remained examined. The proposed control method of the offshore wind farm using voltage source converter high voltage DC is able to ride through a grid fault and release the on grid code request. The simulation results as well expression that the interval of grid fault plays a role in defining the ride-through capability of the wind. The results also shows that the duration of the fault plays a vital part in decision making for wind farm disconnection. Thank you for your listening.